Hello friends, welcome to the session 6 of the real analysis, the continuation of the previous sessions. So in this session we will see the theorems on countable and uncountable sets. So here we study the theorems on similarity of sets, theorems on countable sets and uncountable sets. So the first theorem, we shall see here the statement: prove that every infinite set has a countable subset. So here we need to prove every infinite set has a countable subset. So the proof as follows: let A be an infinite set. Let A be we consider an infinite set A. So that we consider an element A1 in the set A. Because A is a infinite set, the set A is not equal to the singleton set A1. Because the set A is infinite set, the set A is not equal to the singleton element A1, which implies that there exists A2 which is not equal to, there exists an element A2 which is not equal to A1 plus A2 belongs to the set A. Since A is infinite, again A is not equal to A1 plus A2. Since A is infinite, the set A is not equal to the set having the elements A1 and A2, which implies that there exists another element A3 which is not equal to A1 and A1 is not equal to A2, which implies that A3 belongs to the set A. A3, the element A3 belongs to the set A. So if we proceed like this, then the set B has the elements A1, A2, A3, etc., a proper subset of A. So we get the set B a proper subset of the set A. Here A is an infinite set. We get a subset of A, so which is a proper subset of A having the elements A1, A2, A3, etc. If B is finite, then B is countable set. If B is a finite, then B is a countable set. Here we have considered B as a proper subset of A. Therefore, if B is a finite, then B is a countable set. Suppose if B is infinite, then we define a function f from the set of natural numbers to the set B, the subset of A, by f of k is equal to ak, and we can see that the function defined from the set of natural numbers to the set B is a bijective function, which makes the set B a then numerable set, and hence it is a countable set, and hence it is a countable. And the next theorem we shall see: prove that every infinite set is equal to a proper subset of itself. Statement is: every infinite set is equivalent to a proper subset of itself. So you shall see the proof. Let A be an infinite set as it is given in the statement. A be an infinite set. Since every infinite set contains a denumerable subset, because we have proved this in the previous theorem, since every infinite set contains a denumerable set, let B, the set B having the elements A1, A2, etc., A3, etc., be a denumerable subset of A. Let B, the subset B of A, which is A1, A2, A3, etc., is a denumerable subset of A. Let C equal to, the set C is equal to A equivalent to B, then A equal to B union C, then A is equal to B union C. Let the set P equal to the set A minus the singleton set A1 be a proper subset of A. Here we define the set P as a proper subset of A, which is equal to A minus the singleton element A1. So we shall consider the mapping F from A to P defined by f of AI equal to AI plus 1. We shall define a mapping F from A to P defined by f of ai equal to ai plus 1. For ai belongs to B, for ai belongs to B and f of a is equal to a, for a belongs to C, then f is 1 1 and on to function, and hence the set A is equivalent to the set P, and hence set A is equivalent to set P, which makes the union of two countable sets a countable set. And here we have some problems for you. Prove that every infinite set is equal to one of its proper subsets. Another theorem. Prove that every countable union of countable sets is countable. Countable union of countable sets is countable. And prove that the set of all rational numbers is countable. And this is the references for you. Thank you.